In this lecture, we are going to discuss about Taylor's theorem. First is statement. Let fz be analytic. Let fz be analytic within circle C naught with center Z naught and radius R naught. Let Z be any point. Z be any point inside circle C naught. Then fz be represented by an infinite series of the form given by f of z naught plus z minus z naught f dex z naught plus z minus z naught f double dex z naught by 2 factorial plus dot dot dot. Using summation notation, this can be written as fz naught plus sum over n ranges from 1 to infinity z minus z naught to the power n by n factorial f n z naught, that is nth derivative of the function f at z naught, that is fz is analytic within circle C naught with center z naught and radius r naught, and z is any point inside C, then fz can be represented by infinite series of the form given by this series. Now proof. First draw this circle and draw this circle. Suppose this is my center z naught, this is the radius r naught, this is my circle C naught. Z is any point inside the circle. So write consider the circle C naught with center Z naught and radius r naught. Suppose Z is any point inside C naught with inside circle C naught with center Z naught and Z minus Z naught is equal to R. Okay. Then draw a circle with center Z naught and radius capital R. Right. Draw a circle C with center Z naught and radius R such that R naught if W is any point on C, this circle is the C, here radius of this circle is R. So if W is any point in C, W is any point on C, then equation of C is R. This is capital R, not small r. Now FZ is analytic inside C node, inside the circle C node. FZ is analytic inside C. Therefore, by Cauchy integral formula, Cauchy integral formula, we get FZ naught equal to 1 by 2 pi I integration C FZ dz, Z minus Z naught. Next, consider the identity, consider the identity, consider the identity, consider the identity this consider the identity this. Here I am adding and subtracting the same quantity. It will not create any change to the original fraction. Then take minus common. This will be z minus z naught. So it will be equal to 1 by w minus z naught. I'm considering w minus z naught common. This is 1 minus z minus z naught w minus z. Next step, bring this to numerator. We will get this. Bring this to numerator. We will get this one. W minus z equal to 1 by w minus z naught 1 minus z naught by w minus z naught inverse. Next, expand this by using the expansion of this series by using the formula for expansion of this series, that is 1 plus x square. I am here considering the finite number expansion of this series, that is this x to the power n minus 1 by x. You can get this by using the Laurent, not Laurent, it is by using Maclaurin theorem for in real analysis for theta equal to 1. Okay, this is the remainder term for theta equal to 1. Now using this formula I can expand this series, expand this one up to nth term, that is given by this one. So this is equal to 1 by w minus z naught, that is put square bracket, that is 1 plus goes on up to n minus 1. The last term will be z minus z naught w minus z naught and 1 by 1 minus z minus z naught w minus z naught, bracket closed. If I expand this one, I will get this plus z minus z naught by w minus z naught square z minus z naught square w minus z naught cube plus z minus z naught to the power n minus 1 w minus z naught to the power n plus here it is z minus z naught by n w minus z naught to the power n. Look here, if I expand this, that is 1 minus z minus z naught by w minus z naught. This is equal to w minus z naught minus z plus z naught. W minus z naught. This is equal to w minus z, w minus z naught. So if I expand this, I will get this is w minus z by w minus z naught. If I expand this, I will get w minus z, w minus z naught is cancelled out. I will left with w minus z, w minus z. Now here multiplying by fw by fw, multiplying this equation by fw by 2 pi I and taking integral c, integral over c. So I will get this. In the next step, using this formula, I will get this as fw dw, fw dw, w minus z I integral over c, fw w minus z naught dw, then z minus z naught 2 by I integral over c, fw dw, w minus z naught square. Is it? Okay. Next third term. 2 by I integral over c, fw dw, w minus z naught 3 goes on. Third term will n minus 1 term will be then the last term given by to the power n next using the Using higher order derivative, using the formula for higher order derivative for analytic function, we will get, right, using formula for higher order derivative of analytic function, we get what is the formula, that is f of n. If fz is analytic within an on a boundary of a curve C, boundary of a contour C in a domain D, then if z0 is a point inside D, then f and z0 is given by n factorial. All the higher order derivative poses, and it is the formula for higher order derivative is given by this. So using this, we will get by Cauchy integral formula. This is fz and this is fz naught. Then from here we will use derivative of analytic function. Here, mind here, this is 1 by 2 pi I integral over C fw dw w minus z naught. Now here it is 1 plus 1, that is fx z naught by 1. So here I am writing fx z naught. In the next term, it is this one. Here it is 2 plus 1, 1 by 2 pi I fw dw integral over C w minus z naught 2 plus 1. That means this is second order derivative divided by 2 factorial. Goes on. This is f n minus 1 n minus 1 factorial. Wrap this up. The last term will be 2 pi I integral over C fz dz. This is fw dw, not fz dz. This is fw dw divided by w minus z naught minus z naught to the power n w minus z. Consider this term as a SL. goes on up to n minus 1 at term. Put this Sn, where Sn is my nth term. Sn is my this term. In order to get our desired result, in order to get our desired result, we shall have to show that Sn tends to 0, Sn tends to infinity. Sn tends to 0, Sn tends to infinity. It is given Z minus Z naught is equal to R and W minus Z naught is equal to capital R. That is this one. This and this one. Using these two, now find out what is the value of modulus W minus Z. This can be written as modulus W minus, I am adding and subtracting the same quantity. This is equal to this. So using the properties of modulus, I can write, before using property of modulus, you should write this step. W minus Z naught minus, take minus common, this is Z minus Z naught. So using the property of modulus, that is W minus Z naught minus Z minus Z naught. This is from the properties of modulus, and this is equal to my R minus R. Okay. If m is the greatest value of fz in C, then we have modulus Sn is equal to modulus Z minus Z naught to the power n by 2 pi I integral C fz dz W minus Z naught to the power n W minus Z modulus close. Let us check whether it is correct or not. Here it is correct. Then using the properties of modulus of I is 1 and 2 pi is 2 pi. So modulus C fz dz modulus of W minus Z naught and modulus of W minus Z. Now this value is my R. This value is R. And this value is capital R. This value is r minus 1, and this is fz is the greatest value. Modulus. This one is m. This one is r minus smaller, capital R minus smaller. This is capital R. This is smaller. So this further less than Rn by 2 by m by r m by r. Sorry, this is r minus r. This is r minus r. Value of this one is Rn. Equation of the circle C, and this is r minus r. This is m, and this is the length of arc dz. We have already solved this. We have already solved this in the example of complex integral, that this is equal to length of arc. Here is the length of the circle C. This is 2 by m Rn r minus r. The length of arc is the circle 2 by r. C dz equal to 2 pi r, capital R. So this 2 pi cancel out, and we can write this as this is equal to m, and this is r by capital R n. I am writing this with this one. There is one r, and here is r minus r. Since our small r is less than capital R, we have assumed it in the beginning. That is this. That is this. So r by r is less than 1, and consequently this will be converges. So r is less than 1. So if I take n at power n is indefinitely large, so this will converges to 0. Okay, as n tends to infinity. Therefore, Sn converges to 0 as n tends to infinity. That means as n tends to infinity, the sum of the series become absurd, and consequently it will converges to a infinite series. And this series is known as Taylor's series. Okay, z minus z naught fx z naught plus z minus z naught square fx z naught f double x z naught by 2 factorial plus dot dot dot. In summation notation, it can be written as fz naught plus sum over n ranges from 1 to n ranges from 1 to infinity. 1 to infinity z minus z naught to the power n fn z naught divided by n factorial. Okay, which is the required Taylor's theorem. Putting z naught is equal to 0, we get fz equal to f of 0 plus sum over n ranges from 1 to infinity. If I put this equal to 0, then this will be zn. This is n factorial Fn z naught, where Fn z naught is the nth derivative of the function fz at the point z naught, okay, which is known as which is known as Maclaurin's theorem. With that, I would like to conclude. Remaining will be in the next lecture. Thank you.